Welcome to The Explainer. Today, we're going to dive right into the mind of an AI and tackle a really fascinating question.
All right, let's kick things off with a bit of a mystery. You've got a machine, right? And it thinks purely in numbers. So how on earth does it process something visual, like a picture, and something linguistic, like a sentence, at the exact same time? I mean, how does it connect those two totally different worlds? Okay, so let's say we show an AI this picture. To us, it's a bunch of colorful marbles, right? Different sizes, textures, all that. But to the machine, well, it's just a grid of pixels, a giant spreadsheet of color values, basically.
And then we give it this simple little phrase, a bunch of different marbles. For the AI, that's just a string of letters that it chops up into little pieces called tokens. So you've got pixels on one hand and words on the other. I mean, on the surface, that could not be more different.
But here's the crazy part. A modern AI can look at both of those, and it knows. It knows they're talking about the exact same thing. And that is the magic we are going to unpack today. How does it possibly bridge that gap? Let's get into it.
So where do you even start with a problem like this? Well, the first, most intuitive idea is to just smush them together. You just combine or fuse the data from the image and the text.
And it turns out there are a few different ways you could do that. You've got early fusion, which is kind of what it sounds like. You mix the raw data right at the very beginning. Then there's late fusion, where you let each stream do its own thing first, process them separately, and only combine the results at the very end. And yeah, you guessed it, intermediate fusion is just meeting somewhere in the middle.
But there's a huge catch. Just mashing all this data together, it's not enough. It doesn't lead to real understanding. See, the AI doesn't just need the raw data. It needs to get the meaning, the concept behind it all. And to do that, it needs some kind of universal language, a common ground where something like a pixel and something like a word can actually be compared.
Okay, so if just mixing stuff together doesn't cut it, what does? This brings us to what is honestly the absolute core concept of almost all modern AI. We're talking about the language of vectors.
So when the world is an embedding vector, you know what? Think of it like a numerical fingerprint, or maybe a really specific address. It's a way to take any piece of data, doesn't matter if it's an image, a word, a whole sentence, and turn it into a list of numbers. And these numbers aren't random at all. They're like coordinates that pinpoint that concept on a huge, complex map of meaning.
So here's the key takeaway. Our picture of marbles gets turned into one of these vectors, and our text, a bunch of different marbles, gets its own vector too. All of a sudden, these two totally different things are speaking the exact same language, the language of math. They're both just points in the same abstract space.
All right, so, great. Everything's a big list of numbers now. But so what? How does the AI actually use that to figure out that the picture of marbles and the text about marbles are related, but that they're not related to, say, a picture of a cat?
Well, it uses this really clever mathematical trick called cosine similarity. Now, you might think it would measure the distance between the 2 points on our meaning map, but it does something even smarter. It measures the angle between their vectors. Basically, if the two vectors are pointing in roughly the same direction, the AI says, hey, these concepts are pretty similar.
Let's make this super simple. Just imagine our text vector is an arrow pointing straight up. And our image vector, that one's pointing kind of up and to the right, just like these two lines on the graph here.
You can see the angle between them is 45 degrees. And that's the whole game. A small angle means they're really similar. If they were pointing in completely opposite directions, that's a 180-degree angle, the AI would know they have nothing to do with each other.
And just like that, this really abstract idea of similarity gets boiled down to a hard number. The AI literally just calculates a score, usually between 0 and 1. If it's a perfect match, you get a 1. A total mismatch, you get a 0. It's actually that straightforward.
Now, this is where it gets really cool, because this is how models like OpenAI's CLIP actually learn. During training, you just feed the model millions and millions of image-text pairs from the internet, and its entire job, its only goal, is to tweak its own internal brain so that the vectors for the correct pairs get a super high similarity score. That's the bright diagonal you see here. And at the same time, it has to make sure all the incorrect pairs get a really low score. It just keeps doing this, learning by trial and error, until it gets really good at grouping related concepts together.
But of course, there's a catch, a big one. We're not talking about 2 or 3 dimensions like on a simple graph. We're talking about hundreds or even thousands of dimensions. And this leads to this famous, kind of scary-sounding problem called the curse of dimensionality.
The best way to think about it is, imagine trying to find your friend, not in a room, but in a space the size of the solar system. Everything is so incredibly far apart from everything else that the very idea of close or similar starts to break down. It just loses all meaning.
Okay, so with huge challenges like that, how do the latest and greatest models, we're talking the ones inside GPT-4 or Gemini, how do they solve this puzzle? Well, this is where we get to the final and honestly most brilliant trick of the whole process. The big secret is realizing there's a critical fact we kind of glossed over earlier. See, even if the part of the AI that looks at images and the part that looks at text both create, say, a 1,000 number vector, they aren't creating them in the same 1,000-dimensional space. It's like having two different maps of New York City. They're both maps, they both have coordinates, but one is a subway map and the other is a street map. The coordinates from one just don't make sense on the other. They're totally incompatible.
And the solution? It's this incredible piece of math called a projection matrix. The best way to think about this is like a universal translator, a Rosetta Stone. As the AI is training, it doesn't just learn how to make the two separate maps. It also learns to build this special translator that can take any coordinate from the image map and translate it perfectly onto the text map.
So, let's put it all together. Here's the entire flow step by step. An image comes in. A special part of the AI, a vision encoder, turns it into an image embedding. Then, and this is the key, our magic projection matrix takes that embedding and translates it, projecting it right into the text space. And boom, it's now a text-like embedding. The language model can now see it and process it just like it would any other word or token.
And this is maybe the most important takeaway of all. The AI isn't really learning to see images the way you and I do. Not at all. What it's really learning to do is become an expert translator. It's just getting incredibly good at taking the abstract meaning locked inside a bunch of pixels and converting it into the only language it truly understands, the language of text embeddings.
And that leaves us with a pretty mind-bending final thought. We've basically taught a machine to translate our sense of sight into a language it can understand and reason about. So what's next? What would it take to build these same kinds of projection matrices for sound, for touch, for smell? Think about it. We're not just building AIs that can see and read. We're on the path to building a kind of Rosetta Stone for reality itself.